Good morning. Thank you for coming. Today we're going to talk about developing front-end sensors for detection of nitrates and then connecting them up to some remote electronics to allow communication of data to the cloud. So as Brendan says, if you look at this really accurate, precise map of Ireland, Tyndall is located in the People's Republic of Cork, down the very south. Tyndall National Institute is Ireland's largest institute and it's divided into two centres. We have the Microneedle Centre and we have the Photonics Centre. And our expertise really goes across the whole space from atoms up to systems. So we have people in the centre who are looking at theoretical modelling of how molecules bond onto surfaces, which is important in biosensor design, and gate dielectrics. And we work all the way up to smart sensor systems where we actually develop material, integrate it onto devices, take those up devices, and make them in our fab, put them into systems and talk to the cloud. If these are the horizontals of the institute, the verticals that we're working across will be energy harvesting, energy in general, energy management. We're looking at medtech. We look at photonics, and we also look at agri-food, food production. Ireland obviously is an agricultural country. Its highest employer is still in the agri sector, and the Department of Agriculture has outlined some very ambitious targets for Ireland to advance in the next couple of years. And not only has it given targets to the industry, but it's also given this health plan, the Sustainable Health Sharp plan, which is effectively like the ITRS for food production. Okay, so it's a roadmap of where we want to go. And it's broken into a number of different sections that basically ranges from soil quality, all the way up to developing food for health and personalised nutrition. And it's in the, thanks very much. So it's in the soil chemistry part that we're going to have a little bit of a discussion this morning, okay? So one of the ways of improving production on the farm is obviously to digitise the farm, to embed a range of different sensors for different types of things across the whole farming network. So this is a little cartoon. I include the logo of our National Agriculture Development Authority here. We work very, very closely with them. They give us our problem statements and then we work to address those in the ICT world. So there are already, as you know, a number of sensors on tractors, things like GPS, soil monitoring, we have quality, we have yield maps, we have drones flying looking for diseases in fields. But what's not very well known or documented is actually what's happening below the ground, right, in the soil itself. What are the macronutrients doing? What are the micronutrients doing? Are they being taken up by the plants? Are they in a bioavailable format? And that's the area that we just started working in by developing our sensor systems that we've already designed for things like disease diagnostics, and now trying to modify them and apply them to put them into the ground itself. So within the agri space, we have a number of ongoing projects. We're working for disease detection on farm, so a vet can go out and actually measure if a cow has a virus or not. We're looking at contamination in the food products, adulterants in milk, the presence of trace amounts of pesticides or antibiotics. And over here in the environmental side of things, we're interested very much in water quality and in the nutrient, as I discussed, in nutrient flux in soil. And so with that, we're going to discuss. So the way we develop our sensors at Tyndall is we will obviously look at what we're going to sense. Okay, we develop an appropriate sensor. We'll then integrate that with a system that other colleagues in the institute will do, and we'll get a measurement. And most of our measurements that we do, that my group does, are based on electrochemistry. Now, we've had Sandro showed some electrochemical measurements earlier on, so I don't know if these slides are very relevant, but just to explain, if we're trying to detect a molecule, and electrochemistry is all about the movement of one electron from a molecule or two electrons from a molecule onto an electrode. But normally what happens is you have an energy barrier for that to occur, right? So if we want to reduce a molecule, i.e. take an electron from it, or to put an electron onto it, we find that we're energy blocked, so we have to apply a voltage to the system, and then by applying this voltage, we allow the electronic transfer. And the exact same happens, the opposite, when we want to oxidize, when we want to take an electron from a molecule and put it onto the electrode. And it's the movement of these molecules that give us the concentration of the compounds that we're trying to measure. Okay, so to do that, we have a 3 electrochemical cell. As we mentioned, we have a working electrode where all the action happens. We have a reference electrode at which we pin the electrode against, so we know what the voltage is. Sandro nicely showed earlier on that these voltages can shift. We accurately need to know where they are. And then we have a counter electrode that acts as a sink or source of electrons to stop this reference electrode polarizing. And when you put that into a circuit, you end up getting a circuit like this, where you have all these control electronics working in a feedback loop to actually control what's happening on the sensor itself. Okay, so to do soil chemistry, to look at the different components within the soil, initially we were interested in nitrates and nitrites. We decided to use a platform we had actually done and made for interstitial glucose detection, these microneedle sensors that can actually pierce your skin. And the reason we selected those is because they're three-dimensional and they work in a similar way with the soil. So we make these first by using chemically wet machining in silicon. We replicate them in PDMS, and then we pour the polymer solution into the PDMS, cure it and peel it off, and we're left with a polymer replicate of the silicon microneedles. These microneedles effectively have about a 1 micron tip radius, so they're very, very sharp. We can then selectively deposit metals on these microneedles and passivate them, so only the tips of the needles are showing. We do that so we know what the surface area of the electrode is. So here's a little micrograph here on the left of a microneedle. You see the 3 electrodes. You see the reference electrode, which we make by electrodepositing platinum black onto the tips of the needles. That gives us a quasi-reference electrode. We have a working electrode and we have a counter electrode. And here's a cell image of one of those microneedles, and you can see the passivation there ends about there, and the tip of the needle is exposed allowing us to do our measurements. Okay, so to do copper or to do nitrate detection, gold isn't very good, so we electrodeposit copper onto the surface of the electrode. Copper is well known to give you a good reaction to nitrates and nitrites, and we use a high surface area. So you can see this; it's a really rough deposition of copper, which is really good because it will give you higher sensitivity as the nitrate molecules diffuse in and around these copper granules. We calibrated these sensors, so typically people would use a working electrode and a separate counter reference electrode. So we calibrated these in buffer, and you can see we get a nice increase in the nitrate reduction peak with increase in concentration and an increase in the reduction curve. The sensitivity is equivalent to commercial electrodes that you can buy in the shop. So we were very happy with these, and we then proceeded to test them in the environment. So here we have a picture of one of the ponds in one of our local parks, and we took a sample from water from that, and we did a calibration run again across it, and we found that the nitrates in the pond was about twice the limit of what they should be. So the council were delighted when we told them that their water was contaminated. And then moving on from there, then working with other other people in our group sitting over there at the table, we wanted to put the electronics. So I'm a chemist. It's grand for me to go do this analysis in the lab, but I want to go into the field to do them. And we work with these engineers to develop the systems for it. So the core of the system that we took is an analog devices potentiostat chip that was also developed actually for glucose sensing. And we built a number of systems around this in the PCB. We have different interfaces to allow micro SD connections and other external inputs. Anyway, this is the box. And there's our little potentiostat chip. There's our telecommunications, so that will take a GSM card and also work with Bluetooth. It's got various other power connections, and we've got different inputs that allow us to input and output the data from the chip. The nice thing about this, from my point of view, is that we can develop the sensors, and then we can go to this, which pretty much behaves the exact same as an in-lab potentiostat, but allows us direct connectivity to the cloud. Okay, so did I get 12 minutes? Right, I'm going to finish up here just to leave a note at Tyndall in the microanalysis group. We're very much into strategic partnerships. We're really into collaborations. We have a number of different projects ongoing with a range of different types of sensors. These are nanowire sensors. There's micro sensors, depending on what the end case is. We work with other group members or other team members in Tyndall to develop the whole system. So we eventually end up with a full systems package. So we're quite happy to work, collaborate, and to commercialize our products further. And I finally want to give a little call out to next year, where we're hosting the IEEE Nano Conference in Cork. So if you want to come to the Centre of the Universe or People's Republic of Cork, please consider submitting an article to this.